We actually, I have a question. Are
Oh,
you gonna do office hours during Thanksgiving break? Like if we need help?
oh, I'm open to that. So go ahead and email me, and I may be open to that. I'm not going anywhere. I'm basically grading a lot of homework next week. So yeah, so email
Okay.
me, and I'll consider it. Sure.
Okay. Thank you.
Any other questions? Any other questions? Okay. Well, of course, questions in chat. I may have time. I usually have time after class also. All right. Okay. So welcome to. Well, we're ending week 14. We're almost done actually. Right. I have a lot of homework grading to do. That's next week. Right. But right now, today is Thursday, November 19th, day 28. We're going to finish chapter 8 today. All right. So we're going to finish 8.1 on Gaussian elimination with back substitution, GEBS, 8.2 on matrix operations, and 8.4 on determinants. Those are the required sections that you have to do the homework on. 8.3 and 8.5 are optional. You don't have to do those homework assignments. I don't even think I have one for 8.5, but 8.3 is optional. All right, that's on matrix inverses. That's optional. You don't have to do it. 8.5, I don't think I even have any homework, but that's applications of determinants. So remember, you can skip 8.3, and I don't think I have anything for 8.5 anyway. By the way, if you're curious, Tuesday after class, I did this homework problem. Basically 7.1, number 3, ABC. I did that at the end of the Tuesday video. And I'll have time for more questions tonight. Although I know many of you will want to, make preparations for next week. Although the recommendation is that you not travel too much, but I hope that you do have some nice plans next week. All right. Okay. And then after the Thanksgiving break, all right, we're going to do chapter 9 and part of chapter 10, like ellipses, week 15. So a lot of material there. Much of this is either new to you or maybe didn't learn it. You didn't learn it, or you learned it at the very end of your Algebra 2 class. It gets kind of crammed in there. So chapter 9, that's material that a lot of people are going to need to either learn or review. Okay. And we'll do ellipses also. And we'll continue with polar curves and some polar equations on Tuesday the 8th. Okay, and we'll have about a day and a half to cover the homework. And that's a big 250-point homework assignment. Remember, chapters 7 through 10, that's a big 250-point homework assignment. It's a quarter to grade. So make sure you do it well. All right. Again, if you come to class, you keep up. Uh, if you do what you're supposed to do, then it should go well, basically. All right. Any questions before we begin the lecture videos? Again, feel free to put questions in chat. Any questions before we start the lecture videos? So let's begin. All right. We're continuing with 8.1.
Hi, everyone. Let's solve systems using GEBS. All right. So let's solve this system of two linear equations in two unknowns or variables. 4x minus y equals 13 and x minus 2y equals 5. It's a linear system because there are no x squareds or anything, right? Okay, now on an exam, I have the right to tell you to use GEBS as opposed to the other methods of chapter 7. And as a first step, you should write the augmented matrix, maybe by prepping the system first. So for those of you who benefit from putting in the missing coefficients like 1, -1, 0, that could be worth your effort. And if these are not lined up, you should line up your like terms, the x terms, the y terms, the constant terms over here. Okay, so here it's very clear what the augmented matrix is. 4, -1, 13, 1, -2, 5. Actually, going row by row might be better as opposed to going column by column if you're working with the original, because with the original, I think there's more of a danger of thinking there's a 0 there if you're going by column. By row, if you're reading out like x minus 2y equals 5, then I think you're more likely to remember there's a 1. But whatever, start off with this augmented matrix. You don't have to write R sub 1 and R sub 2 there, but I'm using those as guides. Okay, so step 1 is fairly straightforward if you don't make a mistake. Step 2, this is the big one. Now, this is going to take up most of your time, and this could involve some strategizing. After step 2, it's pretty much automatic. But step 2 is the big step. And this is going to take up your time. You're going to apply EROs, elementary row operations, until you obtain the desired form. Ones along the main diagonal and zeros all below. So we're aiming for this. This is kind of like the target back in those trig identities. We're aiming for that form, where the question marks represent kind of like wild cards. Bear in mind, we can get this form if and only if there is a unique solution, one unique solution to the system. And remember the categories, the three categories of EROs. Let's review them. What were they? Row switching or row reordering in general. Row rescaling. You can multiply or divide through a row by any non-zero number. And maybe the addition and rescaling method, in the sense that you multiply, well, bottom line, you can add a multiple of one row to another. You can add a multiple of one row to another, which combines the idea of rescaling and the addition method, the idea of adding equals to equals. Now, you could apply a sequence of steps, get row equivalent matrices in one way to get this. Your friend, your study buddy might do it another way. And you two could both be perfectly correct. In fact, your matrix here might be a bit different from your friend's matrix, and you could both be correct. Now, on an exam, I'm likely to say that I want your final matrix in row echelon form, which means I do want ones along the main diagonal. Some books relax that restriction. And in practice, sometimes it's easier to have these not be ones. But since on the final, I will typically ask for row echelon form for your final matrix. Assuming you can get this form, assuming.
Let me say this loud and clear. I have the, basically on the homework, right? This last homework assignment for chapter 7 and chapter 8 and so forth, chapter 8 here, let's say you must go to row echelon form, okay? I know some people are used to not having ones on the main diagonal, but let's say that I have the right to mark you down if you don't put your matrix in row echelon form, okay? So make sure that if there is one unique solution, you have ones along the main diagonal, okay? So I have the right to demand that, row echelon form, even though it may not be explicitly stated in the homework.
There is one unique solution, I will expect ones on the main diagonal if I'm asking for row echelon form, which I probably will. All right. Now, let's see here. Let's see here. So we have here this matrix, right? And we are going to do what? Our goal is to reach this matrix over here, right? So what do we want? We want to have a 1 in the upper left entry, a 1 in the upper left entry. Now, what's the fastest way of doing that? Think of it. There are a couple ways you can accomplish that. So what are a couple of ways of accomplishing that? Well, one way is that you could divide the top row by 4 or multiply by 1/4. That would be totally legitimate, but then you'd get fractions here, which aren't wrong, of course, but maybe you'd like to avoid them. Can you see an easier way of getting a 1 up there using an ERO? Huh? How about switching the 2 rows? Switching the 2 rows. All right. And that's a pretty quick way of getting a 1 in the upper left corner, which is what we like. Again, I do strongly recommend that you indicate the row operation you're applying somehow. I'm not going to really grade on that, but let's say you get an answer wrong, you get the wrong solution or solution set for this problem. It would help both me and you a lot if you were to indicate what steps you have so that both you and I could look back and try to debug the thing, right? It would help both you and me. So I would recommend doing that. It would help you organize your work and remember what you did. All right. So we have a 1 in the upper left. Great. What else do we need? That 4 in boldface, we need that to be a what? We need that to be a 0. All right. Well, how do we make this into a 0? Switching won't help. You're not allowed to multiply by 0. Remember, don't think about multiplying by 0. You're not allowed to do that. So we're really left with one clear option here, right? Which is that we're going to use that hard to name thing, the addition rescaling method. You can add a multiple of one row to another. We add a multiple of row 1 to row 2 to make that a 0 down there. All right, so here's my question to you. Before you add the top row to the bottom row, what should you multiply the top row by before you add to the result to the bottom row? The goal is to make that a 0. Multiply the top row by what? How about -4, right? So then we get -4 as the multiple, and we get that to kill this off, make it a 0. Instead of doing something, instead of writing something like this, I think this is sufficient, writing the notes down this column. I'd like you to focus on this table. I think this table would be really, really helpful. Again, the goal is to replace into row 2. You need a 0 in that bottom left entry, right? So what you're doing is you're taking the old row 2, that was the 4, -1, 13. The 4, -1, 13. You could put a slash there if it helps. And then you want to add -4 times row 1. Okay, so you go up, -4 times, let's see if, well, let's see here. All right, if you can see that. -4 times 1 is -4. -2 times -4 is +8. -4 times 5 is -20. And again, the reason why I'd rather multiply by -4 than +4 up here is that we're much better at adding. So if we'd like a -4 to knock this out, let's multiply by -4 instead of +4. Let's multiply by -4 and add. We've seen this before with long division, with vectors. We are so much better at adding because that's combining like terms than subtracting. All right. So we add, okay, we get 0, 7, -7. And that's our new row 2. Okay, 0, 7, -7. Wow, we're on our way, right? It's taking some time, but we're on our way. Look at this. Column 1 is good. Column 1 is good. We like the 1 up there. We like the 0 down there. And we'll now move to column 2 and make that good. Remember, the general strategy is that we want to go column by column in terms of making things good, right? Make column 1 good, and then make column 2 good. The idea being, again, let's say you've just cleaned the kitchen floor, you'd be very angry if someone with dirty shoes came in, right? Undoing your good work. Okay, now, the 7. We need what in that position? I want the 7 to become a what? I want it to become a 1. I want 1s along the main diagonal and 0s all below. And how can I get a 1 there? Well, switching won't help really. What about adding a multiple of the top row to the second row? Even though that's a legal operation, what's going to happen if you try that? 1 times whatever, that's going to tend to mess up the 0, right? So really, there's a fairly clear option here. Let's rescale. We want the 7 to be a 1. That means that we either divide by 7, or you could say that we're multiplying by 1/7. Books tend to like talking about multiplying, but you can talk about dividing. We divide through by 7 on the bottom, second row, and we keep the first row. Remember, you're often going to rewrite rows. So we keep row 1, 1, -2, 5. Okay. In terms of what you're doing for row 2, I think this is pretty clear. But some books say the new row 2 gets 1/7 the old row 2, something like that. But we divide row 2 by 7, and we get 0, 1, -1. And we are done, finally, with step 2. Again, your friend might have done it in a different way. Your friend might have gotten different numbers here, and your friend might have been correct. So we are good here because we have a desired form. This is known as row echelon form, and I'll just find that and describe that later on. But this is an example of row echelon form. All right, and bear in mind, computers might actually do it in a different way. Okay, so we've done the hard part, and then from now on, it's really automatic. So remember that if you look at the original system, right, we started with X's and Y's, right? Like the X column there, Y column here, right? Right-hand side over here. Step 3 is to write the corresponding system, the new system. Again, you might want to write these letters to remind yourself, right? Whether it's X and Y or A and B or X sub 1 and X sub 2. All right, so we write the new system. X minus 2Y equals 5. The first row gives us the first equation. The second row, Y equals -1. I like that. We got our Y right there. And why do we like this system? Take a look at the structure of this system. It's called an upper triangular system, which is very easy to solve. Remember, when we were solving 2x minus 1 equals 5, right? Then we kept on going until we got an equation whose solution set was obvious. Here, the solution set was obviously this thing. With this process, with GEBS, the idea is that we get everything down to a system, here, this upper triangular system, which is very easy to solve. Y is -1. What do we do to find X? Take the -1, substitute, plug it in, and solve for X. Y equals -1, plug in, solve for X. Back substitution. GEBS, Gaussian elimination with back substitution. We go up this triangle. So again, when we plug into that first equation, X minus 2Y equals 5, Y was -1. X plus 2 equals 5. Subtract 2 from both sides, X equals 3.
And folks, by the way, show me the back substitution. Don't just do it mentally. Show me the back substitution. I'm giving you the solutions, right?
Which is good to know. Are we done? Hey, we found X. We're done. No, you are not done yet. Remember, you're not always done just with X equals. We have to find Y. All right. Well, wait a minute. We just found Y. -1. Okay. Write the solution in solution set form. Okay, so X equals 3. Y equals -1. Ordered pair, X comma Y, all in braces. Now, when I was saying before, X equals 3, are we done? Well, okay, that's the X coordinate. Remember, that's the second thing we found. It's kind of unusual because I think many of us are used to finding X first, usually. Here, you're finding X second, okay? We're finding X second. And still we have to remember, oh yeah, what's Y? Actually, we had to look up, right? We're going in reverse alphabetical order. If I were really mean and I gave you a system in A through Z, then you're going to find Z first, then Y, then X, and so forth. I think that's a test for road competency. To be honest, I can't do the alphabet backwards sober, so I'm in trouble. All right, anyway, that's the solution set. Observe that the order of the coordinates is the reverse, okay? X comes first, then Y. We're solving for them in reverse order, but you got to put them back in alphabetical order, right? Or whatever order is appropriate, like X1, X2, and so forth. And what can you do? You don't have to, but you can check. You don't have to, but let me tell you something. It feels really, really good if your solution checks out. During exams, I hear little cheers, and I also hear mumbled cursing. So the check can be a very emotional experience, because if it doesn't check out, then you feel kind of obligated to go back and debug, right? But anyway, we could check. Okay, go in the original system before you got your dirty hands all over it, right? It's best to do in the original system. So these are the equations that the thing's got to solve, bottom line. X equals 3, Y equals -1. Plug into these, right? First one becomes 13 equals 13. Second becomes 5 equals 5. The solution checks out. So we feel great. So during the test, we can go, yay. And your neighbor might go, oh, shut up. Boo. All right. A check is optional, but you feel great. Okay, ladies and gentlemen, next time we're going to do 3 equations and 3 unknowns. Doesn't that look lovely? Next time.
Any questions? Any questions? It took me a while to get ready. Any questions? All right, so just as a quick reminder, checking helps. I know the solutions are available in the homework answers, but all right, let's go to 3 equations.
Hi, everyone. Let's now solve a system of 3 linear equations in 3 unknowns. And yes, this could be a lot more work. But overall, the steps are the same, and the overall flavor of the solution of this problem is the same. First up, write the augmented matrix. And perhaps even more so than before, you might want to write in the plus or minus 1s, the 0s, where appropriate, and line up your like terms. For example, remember here that the blank here leads to a 0, right? And we have applied plus or minus 1 coefficients over here. Okay. So here's our augmented matrix. I'll read these off. Row 1, reading off the coefficients, and then the right-hand side. 2, 2, -1, 2. If it helps, I'll write the letters here. X, Y, and Z. Row 2, 1, don't forget the 1. If you see this and you think 0, you might want to write this in. 1, -3, 1, / -28. Over here, -1, 1, 0, / 14. Again, some people remove the slash, especially if you tend to stop at a bar and you don't do what you're supposed to do on the right side. Some of you may benefit from no slash. And again, over here, we have the right-hand side. So this is our first augmented matrix. What's our goal? Our goal is to get this form over here. We want 1s along the main diagonal, 0s all below. Again, that's for row echelon form, which I do technically require. Typically require. And these can be wildcards. And again, you may perform this process appropriately and get 1 matrix. Your friend might perform this process another way and get another matrix. They might be different matrices. It's possible that you can get different row echelon forms that still work. They're still row equivalent. So first off, let's see here. So first off, we want a 1 in the upper left position. We want the 2 to become a 1. And there, whoops. We want the 2 to become a 1. And there are a couple ways you can do this. You could divide the top row by 2. That would work out, but then you get a fraction there. Not horrible, but you would get a fraction there. Actually, another thing we could do is that we can switch these 2 rows. Row 1 and row 2, which you can indicate with a symbol like that, or perhaps a bit more formally like that. I would understand this. Again, it's a matter of debugging so that if you get the wrong solution or I notice you get the wrong solution, we can look back and see what you did. So we switch rows 1 and 2, and don't forget to switch these 2 on the right-hand side as well. We get this: 1, -3, 1, -28. The old row 2 is the new row 1. The old row 1 is the new row 2, 2, 2, -1, 2. And we keep the third row, -1, 1, 0, 14. So we like the fact that we have a 1 up here. Now, these 2 boldface entries, we need to be what if we want row echelon form? We want these to be zeros. How do we do that? We're not allowed to multiply by 0. I don't see how switching is going to help us. So we're going to have to do that rescaling and addition method. So here's what we're going to do. Now, normally, we don't want to do too many operations before we write a new matrix, but you can perform the same type of operation multiple times if you're careful. So for example, we can do that rescaling and addition method to eliminate down this first column over here. So we can make that a 0 and make that a 0. We can perform those operations before we write the new matrix. Okay, so how can we use, say, this +1 to change this 2 into a 0? Actually, you could argue that it might be easier to use the -1 to change the 2, but let's use the +1 here. What would you multiply the top row by before you add it to the second row in order to make this a 0? You would multiply the top row by -2, at least temporarily. We're actually going to rewrite the first row in the next matrix, but temporarily, like over here, okay, we're going to take -2 times the first row and add it to the second row in order to make this a 0. Alternately, you could take twice row 3, add it to row 2. For some people, that's easier, and you could do that. Maybe your friend did that. Okay, here we're going to take the old row 2, the 2, 2, -1, 2, 2, 2, -1, 2, and we're going to take -2 times the first row. So we get, okay, 1 goes to -2, -3 goes to +6, right? -3 times -2 is +6. 1 times -2 is -2. And -28 times -2, I usually allow a scientific calculator on exams. That's 56. When you add down, that's why we multiply the top row by -2 so that we can add here. 2 and -2 gives us 0. 2 and 6 gives us 8. -1 and -2 gives us -3. 2 and 56 gives us 58. That's going to be our new row 2. And if you wish, you could write the new augmented matrix. Well, why not save some time? And let's go ahead and change row 3 as well. Now, bear in mind, I would recommend doing this only down 1 column, to eliminate down 1 column. Don't start moving to other columns. So don't do too much at once. And definitely do not mix 2 different ERO types before you write the new matrix. But here, we're doing that same rescaling addition method, and we're doing it for the purposes of eliminating down column 1. We can do both of these operations before writing the new matrix. By the way, remember that when we write the new matrix, we can use that row equivalent symbol. Okay, so we're going to now change row 3, and we can use row 1 to do that. So, well, I hope we're using row 1 because remember we changed row 2. That might be confusing. So let's take the row 1, all right. and add it to row 3 to make this a 0 over here in the new matrix. The old row 3 looks like this. I'll erase these. The old row 3 looks like this. -1, 1, 0, 14. We're going to, and then we're going to add row 1 to that. And we're not doing anything in row 1. We're just taking it straight up. 1, -3, 1, -28. We're taking 1 times row 1. Add, and we get 0. 1 and -3 is -2. Think Vegas. If you win 1 and lose 3, you've lost 2. That's kind of cheap in Vegas, but 0 and 1 is 1. 14 and -28 is -14. And we have the new row 3. Okay, now we really better write the new matrix at this point. We're going to keep the old row 1. We like that 1 up there, remember? We keep the 1, -3, 1, -28. And then the new row 2 will be 0, 8, -3, 58. And the new row 3 will be 0, -2, 1, -14. Again, this here indicates row equivalence. The matrices are not equal in the sense that you don't have the same entries in the same positions, but they're row equivalent in the sense that they correspond to equivalent systems with the same solution set. Okay, now, we like the fact that column 1 is good. The 1, 0, 0, we like that. So we're now going to fix column 2. And generally speaking, we're looking kind of down and to the right here. We're still going to write these zeros, but I don't think we're going to use row 1 as part of any addition method, because then you're going to mess up these zeros down here. So we're going to tend to look over here. So for example, we're going to tend to use either row 2 to affect row 3 or vice versa. We'll basically leave, we'll basically leave row 1 out of it for now. Okay. Now, there are different ways of approaching this. The way I'm looking at this, in order to avoid having to multiply by 1/4 or something, I might want to use the -2 to knock out the 8, but then you're going to get a 0 right in the center when I'd rather have it down below. So I think I'm going to start by switching rows 2 and 3. You don't have to do that. But let's go ahead and switch rows 2 and 3 so that the -2 is here, the 8 is down there, and then the 8 will eventually become a 0. I'm kind of strategizing. If you don't like that, that's fine. All right. So remember, in the center position, we ultimately, I'll draw arrows. In the central position, oh, sorry, better color. What, brownish? Okay, 8, okay, 8, all right. Okay, so in the center position, the 8 here, well, instead of an 8 in the center, I'd like to have a 1 in there instead of a -2. I'd like to have a 0. Okay, but first, I'm going to switch to the 2 rows here. Okay, which I've indicated here. Row 1, we keep the 1, -3, 1, -28. The old row 3 is the new row 2. The old here I had the 8 here, the -2 here. I'm going to wait, I'm sorry. This is the matrix we're working on. I just copied, right, going from here to here. Okay, so for this matrix, I just copied this matrix and I bold-faced the entries we want to change. So really, the strategy is now, okay, I want the 8. Well, I said this before, I want the 8 to be the 1, the -2 to be the 0. Okay, but then we're going to switch. So the old row 2 becomes the new row 3, and the old row 3 becomes the new row 2. Row 1, we keep the 1, -3, 1, -28. The old row 3 is the new row 2. So we get 0, -2, 1, -14. The old row 2 is the new row 3. 0, 8, negative 3, 58. Now we'll use a row replacement ER row to eliminate the 8. Okay, so by row replacement, that's another way of saying that addition elimination method. We're going to use the negative 2 to knock out the 8, make it a 0. All right, so the old row 3, the one that we're changing up on top here, 0, 8, negative 3, 58. What do I want to multiply row 2 by before I add it to row 3 as this temporary row over here? Negative 2 times 4 is negative 8. That would be a good thing to add. So we take, I'm sorry, it's a positive 4 times negative 2 is negative 8. Positive 4 times negative 2 is negative 8. Okay, so 4 times 0 is 0. Do this. 4 times 0 is 0. 4 times negative 2 is negative 8. 4 times 1 is 4. 4 times negative 14 is negative 56. Okay, and then add down, we get 0, 0, 1, 2. That's our new row 3. Let's replace the old row 3 with the new row 3. We're going to replace the old row 3 with a new row 3. And we get 1, negative 3, 1, negative 28. That's been there forever for row 1. Row 2, 0, negative 2, 1, negative 14. That's holding on from before. But row 3 is changing to 0, 0, 1, 2. So again, column 1 was good from a long time ago. All right. We like the fact there's a 0 here, and we get lucky. We get lucky that there's a 1 there. But even if that weren't a 1, eventually we could divide by, if this were a 3, for example, we could divide by it through this row. Okay, now who's left to change? Who's left to change? We got to change the negative 2. Make that a 1. Don't make it so hard for yourself. Divide by negative 2. Rescale. Divide by negative 2. 1, negative 1/2, positive 7. Okay, so I indicate that division over here. All right. Finally, we have our matrix in row echelon form. We have 1s along the main diagonal, 0s all below. So that ends the really tough part of the problem, right? And your friend may have ended up with a different matrix, but could still be correct. So that's the giant part of the work. Now it's automatic. We write the new system. These are the coefficients for x and y and z. Right. So we write the new system in terms of x, y, and z. From here, the first equation, x minus 3y plus z equals negative 28. Second row becomes y minus 1/2 z equals 7. Over here, z equals 2. We love the system. What shape is it? It's triangular. In particular, upper triangular. We have z equals 2. Great. Now be careful. You don't want these to look too much like each other. Here, I guess it doesn't matter, but I guess I would have written z equals 2. It's a good habit to slash your z's, all right? And then we do what? We back substitute. We take the value for z, plug it into here, and solve for y. And then we're going to take the values that we get for z and y and plug into the first equation to solve for x. Right. That's why we like to have ones along the main diagonal, because then this is 1x, 1y, 1z. Although you could argue it might have been easier in some cases if you avoided the fraction there. But again, I was saying that for our version of Gibbs, we should have ones along the main diagonal, get row echelon form. I also want to teach you row echelon form. Okay, so we do the back substitution. We know z equals 2. We back substitute y minus 1/2 times 2 equals 7. Y minus half of 2 is 1 equals 7. Add 1 to both sides, y equals 8. Not done yet. Take those values for z and y, climb up the ladder. We plug them into here. So I'll clean this up a bit. All right. So y equals 8. Just plug into here. Z equals 2, plugged into here. I guess if your z's and 2's look alike, it doesn't matter too much. All right. So we plug those in, right? Okay. X minus 3 times 8 plus 2 equals negative 28. X minus 3 times 8 is 24 plus 2 equals negative 28. In Vegas, you'll lose 24. Win 2, you've lost 22. Add 22 to both sides. X equals negative 6. We're not done yet. Remember that the answer to solve a system problem is a solution set. And we need to indicate solutions, in this case, in the form of an order triple. Oh, so what's the order triple? What is the solution? Is it going to be 2, 8, negative 6? Is that going to be our solution? No, because that would be in the order z, y, x. That's wrong. That's the wrong order. You have to see, you solve for these unknowns in reverse order. You got to put it in the right order. So you got to reverse the reversal. You start with the negative 6, then the 8, then the 2. When you check your solution, you'll really see that. Again, remember that the order of the coordinates is the reverse of the order in which we found them in the back sub procedure. A check is optional, but you'll feel really good if you see it working out. And really bad if it doesn't, in which case, debug. Maybe it was just a matter of reordering. Hopefully, it would be that easy to fix. You're lucky if it's just a reordering. Okay, check, optional. All right, and remember to check in the original system. X equals negative 6, y equals 8, z equals 2. Okay, we get, hey, 2 equals 2, negative 28 equals negative 28, 14 equals 14, all good. And we're very happy. And your neighbor might still be sad, might hate you. Okay, next up, when does a system have no solution?
All right, any questions before we go on? Any questions? And again, if there's a unique solution, let's say that we require you to get that final matrix in row echelon form. And in the back substitutions, show me how you're back substituting. Questions? Questions? Okay. Next up, degenerate solution sets.
Hi, everyone. So far, the systems we've been solving have had one unique solution, expressed as an ordered pair or an ordered triple. But when does when does a system have no solution? When is the solution set the empty set? It's when you end up with a row that looks like this: 0, 0, 0, /1, for example. Basically, if we ever get a row of the form all zeros on the coefficient side / and a non-zero constant on the right side. Now that happens, you have to stop, or you have the opportunity to stop, and you know right there, hey, the solution set is empty. Because here's the logic. If this system has a solution, then, among other things, 0 equals 1. Wait, this is like the idea of the contrapositive or indirect reasoning. Wait, 0 does not equal 1. So the system doesn't have a solution. 0 does not equal 1. So the system does not have a solution. So for example, let's solve this system. X plus y equals 1, x plus y equals 4. Well, for one thing, they correspond to a pair of parallel lines that aren't the same. But if you do it with matrices, if you try to apply Gibbs, okay, here's the augmented matrix. Now, I know that I keep emphasizing addition, but here, let's go ahead and subtract row 1 from row 2. And we get what? 0, 0, slash 3. We keep row 1. Row 2 becomes 0, 0, slash 3, which would give us the equation 0 equals 3. Nope. The solution set is empty. By the way, I don't even bother putting this in row echelon form. You could divide by 3 to do that. Later on, we'll talk about row echelon form in more general settings. But you don't have to bother with row echelon form in the case where there's no solution, because you can't get our classic row echelon form. All right. Now, if you get all zeros, well, that's like 0 equals 0, which of course is a true statement. It depends on what's happening elsewhere. In this case here, we have the same stupid line, remember? Okay, and we have infinite many solutions. Now, what if we have this augmented matrix here? Well, this guy ruins it. 0 equals 1. Because this equation here this yields the equation 0 equals 0. That guy's kind of chill, but this guy ruins it. In fact, you could have a matrix where you have all these all 0 rows, and then there's one guy that spoils it all, right? Like the weak link. If you see any row that's like that, it's empty set right off the bat. I don't care what happens anywhere else. Next up, let's define the row echelon form for a matrix, and I want you to know it when you see it. So basically, if I give you a matrix, can you recognize if it is in row echelon form or not? And also remember, when we did our Gibbs problems, where there was one unique solution, we went to row echelon form. That's next time.
All right. Any questions? Any questions? All right.
So what is row echelon form for a matrix? Remember, we were aiming for this kind of form back with Gibbs, remember? We have a square coefficient matrix in our examples. 1's along the main diagonal, 0's all below. That's what we were aiming for in our Gibbs problems. This would correspond to a square system with one unique solution. But what if that's impossible? What if we don't have one unique solution? Or what if we have a non-square system? You run into those things all the time in Math 254, linear algebra. In general, what is row echelon form? Well, this is an example of that, but what are some other forms? What are the general properties? So here are the properties of a matrix in row echelon form. And then we'll take a look at this guy. All right, if there are any all 0 rows, there don't have to be any, but if there are any all 0 rows, then they must be sunk to the bottom of the matrix. Now, aside from such rows, every row must have a leading 1 as the leftmost non-zero entry. So you can have a bunch of zeros, and then the first non-zero entry has to be a 1, not a 2 or a 3. And these leading ones must flow down and to the right. They could be on a straight diagonal. They don't have to be. They don't have to be on a straight diagonal, but they generally have to go down and to the right. You could not have a leading one here and then a leading one over there. Okay? You can't have that. So take a look at this. Is this matrix in row echelon form? Well, there is a row of all zeros, and sunk to the bottom, Again, you don't have to have an all zero row, but if you have any, they must be sunk to the bottom. The leading non-zero entries are all ones. This is a leading one. Bunch of zeros, leading one. Bunch of zeros, leading one. So the leading non-zero entries are ones, and they generally go down and to the right. Not necessarily on a straight diagonal, but they generally go down and to the right. Again, you never have a leading one like that and a leading one like that. You'd have other ones. I mean, this one is fine, but it's not a leading one. Often we do circle the leading ones in a matrix problem. They can help us in operations. Okay. So this is in row echelon form. Now, there's a specialized form called reduced row echelon form, RRE form. And in particular, those are helpful in linear algebra in cases where you have infinitely many solutions. Also, it's a function of a matrix. If you give me a matrix of size m by n, whatever, and it's full of numbers, right? There's only one reduced row echelon form. Just like when we were talking about Gebs getting us this matrix over here, I said that you might get one row echelon form, your friend might have another row echelon form. Row echelon forms in general are typically not unique. I mean, if you have a matrix of all zeros, well, you have all zeros, that's it, right? But usually row echelon forms for a matrix are not unique. But every matrix with numbers in it only has one reduced row echelon form for a matrix. In that sense, it's a matrix function. In MATLAB, you have RRE, or programs might have RREF. So MATLAB is called Matrix Laboratory. It's a common program. And it has either RRE or RREF. Now, what are the properties of a matrix in reduced row echelon form? Well, it's got to be a row echelon form matrix. But on top of those properties, each leading one has zeros, not just below, which would be true for a row echelon form, unless the one was already on the bottom, right? But the leading one would also have all zeros on top, if anything. So each leading one has all zeros elsewhere in its column. Or in other words, each leading one is the only non-zero entry in its column. So let's take a look here. Well, let's take a look at this matrix. Erasing these. Take a look at this matrix. How many of these entries would have to go to zeros in order to make this row echelon form matrix a reduced row echelon form matrix? How many entries and which ones would have to go to zeros? Look at the leading ones. This one is already on top of his column, and of course we have zeros down here. This one has zeros below, but in order to get reduced row echelon form, this 7 would have to go to a 0. This leading one has got a 0 below it, but we have to change these entries to zeros using elementary row operations. Don't just go in and make them zeros. You need EROs. And by the way, to get zeros here, you would eliminate up. You would use lower rows to help eliminate entries in higher rows. So for example, you could use the 1 in row 3 to hit the 9 in row 2. And then these zeros don't change anything up here, from here to here. And this one could also be used to hit this 4. This one would be used to hit this 7. And then if you go right to left in terms of fixing the columns, there are no leading ones over here, then you can change these to zeros, and then it becomes easier to change that 7 guy. Okay. Now, in Gauss-Jordan elimination, And you don't have to know this, but this is an alternative to Gibbs. It's kind of a Gibbs with additional pieces to it. Gauss-Jordan elimination is a matrix-heavy alternative to Gaussian elimination, in which we use elementary row operations to go all the way to RRE form. So if you love matrices and you hate letters like X, Y, and Z, you might prefer Gauss-Jordan elimination, and some students do use it. On a final exam, I would typically say on a matrix solve a system problem, you can solve the system using Gibbs or Gauss-Jordan elimination, which again can be thought of as Gibbs with some more pieces to it, or even a form of Gibbs, where you actually eliminate up sometimes. Gauss-Jordan elimination. All right, again, I mentioned before, MATLAB is a popular program that uses, it's RREF, it's RREF, a command that gives you the RRE form for a matrix of numbers. Okay, so here's the idea. Again, you will not be required to use Gauss-Jordan on the final. You can use Gibbs in general. If you know Gibbs in general, you won't be required to know the particulars of Gauss-Jordan on top of it. But, okay, here's the idea. Let's say that you have a system and it leads to this augmented matrix, okay? Now, if you're going to use Gaussian elimination, then we're in row echelon form, right? This isn't row echelon form. You can then write the system in, say, X, Y, and Z, back substitute, and so forth. But if you want to use Gauss-Jordan elimination, then you also have to eliminate up. Use this 1, eliminate 3, eliminate this 3 also. Use this 1, eliminate the -2. And if you do that, you end up with, I show the operations here, you end up with this over here, which, by the way, is the unique reduced row echelon form for this thing up here, and also the guys below him. Okay, now what's one key benefit of Gauss-Jordan elimination? Because you might be going, wow, I did all that work with matrices. What's my reward? What's my reward for that? Look at this. What's your system? Write the system for this. A, x equals 1, y equals -1, z equals 2. It's right there. Basically, you can read off entries on the right-hand side, and you can ignore this row of all zeros down below. Although we tend to keep it in the actual matrix. We usually don't knock out an all-zero row just because we feel like it, but here we can ignore this when we're stating the solution. Again, well, right here, x equals 1, y equals -1, z equals 2. That gives us an ordered triple, x, y, z, 1, -1, 2, an ordered triple in braces. So you see, it is true that you have to do more work with the matrices, but hey, once you get all the way to reduced row echelon form, you can essentially read off the coordinates of the solution off the right side, with maybe some modifications, like ignoring this 0 row. I won't talk so much about part I. So here's an example where you end up with a solution set with infinitely many solutions. You might see this kind of thing in Math 254, linear algebra. And if it does have any solutions, it'll be of this form, x, y, z, w. And it turns out that, again, for this system, it helps to put it in RRE form, meaning use Gauss-Jordan elimination. So then we go all the way down to this RRE form. You write down the corresponding system. You parameterize the free variables, which do not correspond to the leading 1 columns. You parameterize the y, meaning that you do something like you let y equals a, w equals b, right? Solve for x and z, et cetera, and you get a solution set of this form. Again, you won't see a problem like this on our final, but essentially what you end up with is, get this, this represents a hyperplane, a 2-dimensional hyperplane in 4 space. That sounds like a Star Trek thing, but if you're interested in in that idea, a solution set that's a two-dimensional hyperplane in 4 space, A, go read this part. A and B vary over the reals, and that gives you a two-dimensional solution set. Okay. Next time in 8.2, we'll talk about matrix operations in general. You don't have to talk about solutions, or sorry, you don't have to talk about systems all the time. We see matrices elsewhere.
Any questions on 8.1? Because I'd like to do the first easy video on 8.2, then we'll take a break and we'll continue with chapter 8. Any questions before we do the first video from 8.2? Any questions? Any questions? Okay, lots of practice on the homework. Any questions? All right, one video from 8.2 before we break.
Hi, everyone. You know, we can use matrices outside of systems. We can use matrices just as boxes of numbers, like we often do in statistics. So let's talk about matrices in general. And these won't even be augmented matrices for the most part, just box of numbers like these. Oh, these represent numbers. So some notation. We often represent a matrix by a capital letter, like capital A, capital B, and so forth. This says that the matrix A consists of entries that we can label as A sub I j, where I is the row number and j is the column number. So for example, in this 2x2 matrix, and often in linear algebra, math 254, you would write out this kind of notation. In the upper left, A sub 1, 1, row 1, column 1, row 1, column 1. A sub 1, 2, row 1, column 2. A sub 2, 1, row 2, column 1. A sub 2, 2, row 2, column 2. Now for huge matrices, which you might consider more abstractly, you might use columns. For example, if you have you could have, for example, A sub 10, comma 10, if you have a 10 by 10 matrix. Although I'm sure you wouldn't write out all the entries explicitly. Now, A sub 1, 2 and A sub 2, 1 are not necessarily equal. If they are, then we have a symmetric matrix. Here's an example of a symmetric matrix, which is extremely important in higher math and linear algebra. Not so much in our class. So for a symmetric matrix, the idea is that when you look at the main diagonal, right, the entries that face each other across the main diagonal are equal. So the 3's here face each other. Symmetric matrices are extremely useful in higher calculus, statistics, and so forth. They have great properties. Okay, finally, when does A equal B? Before with our ER rows, we were doing row equivalent matrices, but when are two matrices actually equal? Well, A equals B if A and B are two matrices, if and only if they have the same size, m by n, and they have the same numbers or expressions in the same positions. So for example, here, these are both 2x2 matrices. Upper left has 1, upper right has 2, lower left has 3, lower right has 4. Same numbers in the same positions. So if you look over here, even though these two matrices have the same entries, they're in different positions. Two of them are in different positions. The 2 here and the 3 here, they switch positions, which means that these matrices are not equal. They have the same entries, but in a way in a different order. Two of them are in a different position. Now, if this is the matrix A, then there is a relationship between these two matrices, and we can describe the relationship as the transpose relationship. If this is A, then this is A transpose. And why is that? Because the rows of one matrix are the columns of the other matrix. And the rows here are the columns here. Over here, if we consider these as matrices, this matrix is 1 by 2, and this matrix, and this matrix is 2 by 1. Now, sometimes we might think of this as a row vector, and sometimes we might think of this as a column vector. And by the way, these are transposes of each other. Incidentally, what kind of matrix is equal to its transpose? I'll give you a hint. We've seen one before. This guy over here. If you make the rows the columns, well, you get the same matrix. You get the same matrix, right? So this matrix is its own transpose. That defines what kind of a matrix? Defines a symmetric matrix. You don't have to know that for our final, but in linear algebra, Math 254, that can be a useful fact. It will be a useful fact. It's the way that you can succinctly define symmetry, a symmetric matrix. Okay. Next up, we're going to talk about basic operations for computing with matrices, and they're not so surprising. Next time.
And of course, we don't have a final exam. We have final homework, but it's 250 points. So it's a big final assignment. All right. Okay. So we're going to go on with chapter 8. It's 8:12 right now. So let's take a break until 8:23. All right. So come back at 8:23 p.m., obviously. All right. And I'll remember to mute now, and I got to remember to unmute, and I'll record. But remember, mute now. Okay, I'll see you at 8:23 p.m. We'll continue with chapter 8, all right? All right, let's continue on. 8.2, continuing.
So now we're going to talk about basic operations with matrices. And these are fairly straightforward, but still the examples will be helpful. In matrix addition, first of all, the two matrices have to be the same size. Otherwise, the sum's undefined. But if the matrices are the same size, then you add them by adding corresponding entries in the same positions. For matrix subtraction, well, you add the opposite, like usual. Scalar multiplication, just like with vectors, to multiply a matrix by a scalar, or a real number, you multiply each entry of the matrix by the scalar, like with vectors. So for example, if we have these three matrices, which are all 2 by 3, 2 rows and 3 columns. So right off the bat, we could, for example, just add all of these, and that sum would be defined. Now notice here, B is interesting. B is the 2 by 3 zero matrix consisting of all zeros. And it's the additive identity in the sense that if you add this matrix to any other 2 by 3 matrix, you get that other matrix. However, even though it's the additive identity, it's not what we call an identity matrix. That's a multiplicative identity. We'll talk about those later. They look different. Okay, let's do it. Let's find some. Let's find some matrices. Here's a matrix expression: A plus B plus 2C. First off, in case you forgot, how dare you? Let's replace A, B, and C by what they were, right? In numerical form, right? In the brackets. A was this matrix. B was the zero matrix here. C is this matrix. Over here, well, if you perform matrix addition, just like we said before, this is the additive identity for all 2 by 3 matrices. So when you add these first two matrices, you get the first matrix. Over here, when you take twice a matrix, you multiply each of the entries by the 2. You double each entry. So you get 2, 4, 0, 0, 2, -6. When you add these matrices, add the entries in corresponding positions. 2 plus 2 is 4. 0 plus 4 is 4. 1 plus 0 is 1. -1 plus 0 is -1. 3 plus 2 is 5, and 2 plus -6 is -4. There you go. Now, this is not so vulnerable to avalanche effects in the sense that if you make a small error somewhere, it may haunt you in that entry, but not so much in the whole matrix. Whereas before with things like Gebs, if you made a mistake early on, it could really hurt you in all sorts of ways down the line. Find A minus 5C. The key point I want to make here is that if you're basically subtracting a matrix or subtracting basically if you're subtracting a matrix and there's a number here, right? Okay, you might want to think of matrix subtraction as adding the opposite. So instead of A minus 5C, we can think of this as A plus -5 times C. So over here, here's the matrix C. We can start by multiplying by -5. In a way, it's kind of a distribution. You multiply each of these entries by the -5, you get these. And again, to add matrices, you add corresponding entries in corresponding positions. 2 plus -5 is -3, 0 plus -10 is -10, 1 plus 0 is 1, -1 plus 0 is -1, 3 plus -5 is -2, 2 plus 15 is 17. Again, there you go. And if you make a mechanical error, I'll tend to be fairly lenient. But don't make too many of them, though. Next, we're going to talk about how to multiply vectors and matrices. And it's not quite as easy as you might think, but we are going to see some familiar operations next time.
Okay, any questions thus far? Any questions? Because matrix multiplication is not component-wise. It's not quite what you think. It's something else familiar. Any questions? Any questions?
Hi, everyone. In order to multiply matrices, we first have to talk about multiplying vectors. In particular, a row vector times a column vector. So let's say we have a row vector like this with n entries, and a column vector like this with n entries. You have to have the same number of entries. Well, this may sound familiar. When you multiply the row vector by the column vector in this order, don't switch these. It goes this times this, plus this times this, plus this times this, plus this times this, plus this times this. And you can think of the result as either a scalar or a 1-by-1 matrix. It depends on the context. But does that sound familiar? This times this, plus this times this, plus this times this, da da da. It should remind you of a dot product. So when you take a column vector, sorry, a row vector times a column vector, then here you get 1 times 4 plus 0 times 5 plus 3 times -1. Again, remember for dot products, if you're like me and you tend to miswrite things, you might want to write down the products without writing all this, whatever works for you. 4 plus 0 plus minus 3, we get 1. Either 1 or the 1-by-1 matrix containing 1. Again, it depends on the context. Basically, it's the idea that the dot product yields a scalar, basically. Oh, and incidentally, it turns out that if we had a column vector times a row vector, we get something very different. It turns out that we get, well, we'll see. It's the multiplication table. It's the multiplication table. We'll see. All right. So now we can multiply matrices. And you might think, well, why not do what we did with matrix addition and just add corresponding, well, just as with matrix addition, just as we added corresponding entries, why don't we multiply corresponding entries for matrix multiplication? Well, MATLAB does have an operation for that, component-wise multiplication, but matrix multiplication is different. And it actually corresponds basically to linear transformations in linear algebra, Math 254. So first of all, when can we multiply matrices? Well, just like with matrix addition, it really depends on sizes, but in a different way.
Okay, actually, I should have said compositions of linear transformations, but you won't know that till 254 anyway.
So our first question is, when can we multiply two matrices, and what would the size of the resulting matrix be? And then if the matrix product is defined, how do we get that matrix product, entry by entry? So the first issue here, given two matrices A and B, the matrix product AB is defined if and only if the rows of A and the columns of B have the same length. This makes sure that the dot products work out. Now, that means that when these have the same length, it actually means that the number of columns of A, the matrix on the left, is equal to the number of rows of B, the matrix on the right. I'm doing this because it turns out I'm going to multiply matrices using a trick. Now, if this is confusing, I don't blame you because there's actually a better way of doing it. I should have mentioned that. You don't have to freak out too much about this. Let's talk about some tricks here. Consider the matrix product A times B in this order, where A is this 2 by 3 matrix over here, B is this 3 by 2 matrix over here. So again, we're going to ask, is AB defined? Is this matrix product defined? And if so, what is its size? So let's consider the sizes of A and B. We just observed A has 2 rows and 3 columns, so A is 2 by 3. B has 3 rows and 2 columns, therefore B is 3 by 2. The matrix product is defined because these 2 middle entries are equal. That corresponds to the notion that the number of columns of A is equal to the number of rows of B, meaning that when you consider a row, basically the length of the row equals the length of the column, so you can do dot products. But again, the number of columns of A equals the number of rows of B. But just observe and ask yourself, are these 2 numbers here in the middle equal to each other? If so, the matrix product is defined. And given that this matrix product is defined and AB is defined, what is the size of AB? What is the size of that matrix product? Well, take a guess. Take a guess. It's going to be 2 by 2. It's determined by the outer numbers. So if the inner numbers are equal, the size of the resulting matrix product is given by the outer numbers in that order. So AB is 2 by 2. In general, because you might be wondering, well, what if it's not square? If A is m by n and B is n by p, then well, first of all, the matrix product AB is defined because n equals n. These 2 middle numbers are equal. Given that this matrix product is defined, it turns out AB will be m times p. You might go, well, that's cute, but why is that? Well, when I show you the trick for multiplying matrices, we'll see why this is. Why it's the number of rows of A by the number of columns of B. We'll see why that is. Okay, now, if a matrix product is defined, how can you find the entries in that matrix product? You don't do it by just multiplying corresponding entries like we did for adding and addition. It's different. We take dot products. So, and remember, you don't have to remember this. I'm going to show you a shortcut, but here's the long way, the harder way. If AB, the book way, if AB is defined, then the entry in its ith row and jth column is the ith row of A times the jth column of B. Do you think you can really remember that? Me neither. I don't think I can remember that. So there's a shortcut. This is true, but there's a shortcut, which works a lot easier for me. Okay, so we're going to go back to the two matrices. Wait, do I have? Oh yeah, we have the two matrices here. Okay, we established that AB is defined. The result will be a 2 by 2 matrix. But what are the entries? All right. A traffic intersection model, streets. So here's the idea. We want the matrix product AB in that order because BA is a different deal. The matrix product AB. The matrix A on the left, I'll put here. The matrix B, I'll raise up here. And then lightly draw these horizontal lines through the rows of A. Not too thickly though, because you don't want to cover up the negative signs. I know this seems kind of strange, but you have to worry about stuff like that. And draw columns, draw these vertical lines through the columns of B. But again, draw them thinly, not too thickly, because you don't want to cover up ones and things like that. Strange considerations. Now here's the idea. Here we have the matrix AB. And right off the bat, you can kind of see why it makes sense that AB will be 2 by 2. Because here's the deal. We're going to take the dot product at each of these positions. I'm going to call this matrix product AB C as a single letter. So then this is C sub 1, 1, and so forth. Now for C sub 1, 1, the upper left entry, top left entry, we take the dot product of the first row of A and the first column of B. The bottom line is you're going to take the dot product of the vector, the row vector, and the column vector whose corresponding lines intersect here. So for this entry, you take the dot product of this row vector and this column vector. That's easier to remember than it's the first row of A times the first column of B. So we do that. Now, it makes sense that, first of all, AB is defined because notice that the row length of A equals the column length of B. That ensures that we can take dot products. And the row length here is the number of columns. The column length here is the number of rows. So the number of columns here equals the number of rows there, which means that the matrix product is defined. But again, instead of worrying about that, okay, we had that earlier trick, right? Those two middle numbers were equal. Okay, right? That was the bottom line. The two middle numbers are equal, right? Two middle numbers are equal. And the result is 2 by 2, the number of rows of A times the number of columns of B. Look at this. Well,
I say
rows, no, the 2 rows of A will give us 2 rows in here. The 2 columns in B will give us 2 columns in here. And it'll be a 2 by 2 matrix. So here you can see it better. An M by N matrix times an N by P matrix will give us an M by P matrix. Number of rows here by number of columns there. All right, so then we actually take the dot products. And I'll go through the rhythm with you. Let's go through the rhythm. Okay, so for C sub 1, 1, all right, the upper left entry, okay, the dot product is going to be, let's see, green. It's going to be first row times first column here is going to be this times this, plus this times this, plus this times this. Again, if you're like me and you tend to miswrite things, you might just want to work the products in your head and write them down. Some of you might want to write all this, but it's going to be, think products, 4 plus the -3 plus the 0. If either of these is a 0, the result is 0 for that product. But it's 4 minus 3 plus 0, which is 1. So a 1 goes in the upper left entry. And then I'll show you the rhythms, okay. For the upper right entry is going to be the first row of A times the second column of B is going to be this times this, plus this times this, plus this times this. So it's going to be, all right, the -1 plus 0 plus 0, -1. -1 over here. C sub 2, 1. Row 2 of A times column 1 of B. Don't worry about that. Just work the streets here. Work on the streets here. All right. So for this entry here, 2 times 4 plus 1 times 3 plus 3 times 1. All right. So we have 8 plus 3 plus 3. 14. All right. And then bottom right entry, second row here times second column here. It's going to be 2 times the -1. Oops, here. 1 times 0, 3 times 2. What are the products? -2 plus 0 plus 6, which gives us 4. All right. So you put these in their correct slots. Oh, and by the way, I would not expect you to necessarily do it like this. In fact, I would accept answer only, although I think it would help you to do some work just for accuracy's sake. But the answer turns out to be this. I would accept answer only, but the thing is, you want chances for partial credit. And of course, our arithmetic can often fail us when it comes to speed, right? But bottom line, here's the matrix product. 1, -1, 14, 4. Do make sure that you're putting the correct numbers in the correct positions. Okay, so be careful about that. It's wrong if you put them in the wrong positions. Okay. Now, warning, matrix multiplication is not commutative. You could consider A times B and B times A, and they may not be equal. In fact, it's possible that one might be defined and the other is not. So AB and BA could look very different, or one could be undefined even, or both. And again, why is matrix, and think about it, when are they both defined? I'll have you think about that. Why was matrix multiplication defined this way? Well, it's related to compositions of linear transformations, which you'll see in linear algebra. Next up, identity matrices. And these are very important in linear algebra. Basically, what kind of a matrix acts like 1? Next time.
All right. Any questions so far? Any questions so far? All right. That's matrix multiplication. All right. Going on. What kinds of matrices act like 1?
Hi, everyone. So what kind of a matrix acts like 1? Well, we talked about a zero matrix before, something with all zeros in it, right? But what matrix acts like a 1? Well, this may not be obvious to you, but it's this over here. A matrix with 1s along the main diagonal and 0s everywhere else. And what form is this matrix in? It's a really great example of what kind of a form. Not just row echelon form, but reduced row echelon form, RRE. Leading 1s all over here on the diagonal, 0s everywhere else. So for example, I sub 3 is the 3 by 3 identity, 1s along the main diagonal, 0s everywhere else. In general, I sub n is the n by n identity. These matrices are multiplicative identities, just as the zero matrix here was an additive identity for 2 by 3 matrices. These matrices here are multiplicative identities in that they play the role of 1. In the sense that when you multiply by 1, you get the original thing back. In this case, if you multiply this matrix by any compatible matrix on one side or the other, meaning that the matrix sizes work out when you do products, then you're going to get the other guy. So in that sense, it acts like 1. Multiply by this, you preserve the other guy. just like 1 times 3 is 3. Play with it, see why that is. If A is an n by n matrix, then A times the n by n identity is A, you get A back, and also in reverse. We do have commutativity. Square matrices commute with their corresponding identity matrices. 3 by 3 matrices will always commute with these, meaning that the order doesn't matter when you take products. Again, although matrix multiplication is not in general commutative, it is true that the identity matrix commutes with a matrix of the same size. And in fact, even if you have a non-square matrix, like over here, as long as you have compatibility, you'll get this guy back. Okay, now, where can matrix notation help us in terms of solving systems of linear equations? Let's say we want to solve this system. And I know it might be a bit disorienting because we don't see x, y, and z. We see x sub 1, x sub 2, and x sub 3. A system of 3 linear equations in 3 unknowns. Now, believe it or not, we can write this system in a matrix vector form. Ax, sometimes x is written like this, like the way we used to write vectors. Ax equals b, another vector. Ax equals b. Or you can think of these all as matrices or as a combination of matrices and vectors. A times the vector x equals the vector b. Now, if you don't see why that is, remember that old trick, if you raise this thing up, well, you don't even have to do that. For example, how do we get that first equation? Imagine taking the dot product of this and this. 1 times x1 plus 1 times x2 minus 3 times x3, that's the left-hand side here, equals 9. And so forth. From the second row, and these variables equals 6, we get that. Over here, x1 minus x2 plus x3 equals -5. So this is really convenient. It works out. And this is, incidentally, the coefficient matrix. See, if you had done the augmented matrix, A slash B, if you had done the augmented matrix, hey, coefficient matrix goes here, right-hand side goes here. All right. Now, what if we perform Gauss-Jordan elimination to A slash B? Again, it might be using this vector notation. So Gauss-Jordan, that means that we have to take this thing to reduced row echelon form, REF, reduced row echelon form. We want to go to that. And it's unique. Remember, each matrix has only one unique reduced row echelon form. Okay, so again, we're setting up this augmented matrix the way we used to, way back in section 8.1, right? If you had done, right, basically the way you did this old school in 8.1, this thing here, I'm writing over here, A slash B. Our old school augmented matrix from 8.1. Haven't seen him in a while. Now, if you take this to row echelon form, you get that. So if you're doing GEBs, you can go to here and then write the system and back substitute, right? So it's an upper triangular system and back substitute. That's for GEBs. You can solve a system that way, assuming there's a unique solution. And there is here because, see here, if you have, we have this in that old school row echelon form. But I said go to Gauss-Jordan. If you go to Gauss-Jordan and you eliminate up, they end up with this. Now again, on the final, I will not require you to use Gauss-Jordan, but take a look here. Interesting. So on the left side, who is that? Who is that? I sound like I own a pet. This is I sub 3. It's the 3 by 3 identity. And guess what comes over here? Well, what happens, right? If you work this out, right? The unknowns were x sub 1, x sub 2, x sub 3. I'll write that. X sub 1, x sub 2, x sub 3. X sub 1 equals 0, x sub 2 equals 3, x sub 3 equals negative 2. All right. Well, hey, looky here. We get the coordinates of our solution. You know what this is? This is x. It's our solution for x. It's a solution vector. It's x as a solution vector. Pops up over here. We mentioned this before with Gauss-Jordan, that if you can get it into this great a form, you can read off coordinates just on the right-hand side. Instead of using braces, I'll express this vector as just a column vector, 0, 3, negative 2. It's assumed that we know that this is x sub 1, the value for x sub 2 here, value for x sub 3 here. And you can check. All right, so what is Gauss-Jordan? I talked and rambled on about Gauss-Jordan. We start with this, the old school first augmented matrix from 8.1. What's Gauss-Jordan? You go from here to here, pretty cool. Assuming that you have one unique solution. You can only possibly get the identity matrix there if there is one unique solution, assuming it's a square system. Otherwise, it's impossible to get that. All right. So at the end here, I was basically connecting matrix notation and solving systems. So next time, well, what are some other ways of looking at this? We have AX equals B. Could we solve for X? In a way, yeah, just from this formula. Next time, inverse matrices.
Now, bear in mind, the next section, 8.3, is optional. You don't have to do any homework on that. But still, it's good to preview that. So let's look at that. Any questions? Any questions? Feel free to put questions in chat. Again, 8.3 is optional. All right.
Hi, everyone. Section 8.3 on the inverse of a matrix, in particular, square matrices. This is cool stuff, but it's optional. It won't be on your homework or any test or anything, and you can pick it up in linear algebra, Math 254. Well, let's go over some ideas here. All right, so let's say that you have A, where A is not 0. What is the multiplicative inverse of A? A times what will give you 1? A times what will give you 1, all right? Well, A times its reciprocal will give you 1. 1 over A is A to the negative 1. For example, if A is 3, what's the multiplicative inverse of 3? Well, 3 times what gives us 1? 3 times a third gives us 1, the reciprocal. So likewise, what's the deal with the inverse of a square matrix? Well, if A is a square n by n matrix, there sometimes exists a matrix A inverse. Remember up here, 0 did not have a multiplicative inverse. Some matrices don't have inverses. But if the matrix is invertible, then A times A inverse will give you the identity, which acts like 1 in the world of matrices. And also, the inverse commutes with the matrix. A inverse times A is the identity, like 1. So the procedure to find it is basically making a big block matrix, A slash the identity. I'll show you that. And then you go to reduce row echelon form. So basically, if I give you this matrix, it's a big block matrix. You put this matrix over here. The identity, you put this big old 3 by 3 thing over here to the right of the slash. Do Gauss-Jordan, take this to RRE form. It'll take a while. But again, this won't be on your homework or exams. And you end up with this. The identity is on the left. If the matrix was invertible, you can get the identity on the left. A inverse is on the right. If you want, you could check, but it might take a while, showing that A times A inverse is the identity, or the other way. Now, you can use inverse matrices to solve systems. For example, back in Algebra 1, right, you have AX equals B, right? Assume A is not 0. Well, how would you solve for X? You divide both sides by A, right? In other words, you multiply by what? You multiply by the reciprocal, the multiplicative inverse of A, 1 over A. And then you basically get this. But now, what's this? Oh, okay, here I'm writing 1 over A as A to the negative 1. And for matrices, it looks similar. Assume that the matrix A is invertible. AX equals B, all right? Left multiply on both sides by A inverse. Remember, matrix multiplication is not commutative. So when I say multiply by A inverse on both sides, I have to specify on the left. A inverse times A is the identity. You have compatibility here. I times X is X. X equals A inverse B. And that's a way of solving a system, assuming you have one unique solution. And it's a square system. So for example, if you have software and you don't know if it has a solve a system function or things like, or anything like that, then you could try these matrix operations. And there are ways of finding shortcuts for a 2x2. We won't cover that. Okay, that was optional, but fun.
Right. Now, 8.4 is not optional. You have to know that stuff and do the homework for 8.4. All right. So questions, well, any questions? 8 through is optional. Any questions? 8.4 next is required. Required.
Hi, everyone. In section 8.4, which is required, definitely, we're going to talk about the determinant of a square matrix, which is usually a number that we associate with a square matrix. And later on, we'll talk about its applications to area and volume. So every square matrix consisting of scalars, in particular real numbers, has a determinant. And we can denote that by det of A, or A with the double bars around it. Again, the determinant is a scalar or a real number. Now, some people might confuse these with absolute value. It does not mean absolute value because, for example, determinants can be negative. So if you find this confusing, use det of A. We're going to start with talking about shortcuts for computing determinants. And by the way, determinants, as far as they go, the key question is whether or not they're 0. Or maybe they're close to 0. Basically, if a determinant is close to 0, things are kind of messed up. All right, some shortcuts. Well, not surprisingly, if you have a 1-by-1 matrix, like this thing, the determinant will be the entry. So if A is the matrix consisting of 7, the determinant of A would be 7. This is where the absolute value confusion can come in, because if, for example, the entry is -7, then the determinant would be -7. This might look weird to some people. If the matrix is 2-by-2, you get the determinant by what I call the butterfly, the product along the main diagonal minus the product along the skew diagonal, AD minus BC. Now, the shortcut for 3-by-3, this is given in some books, but not all. Sarris's rule, named after Pierre Sarris, actually. So for a 3-by-3, so this seems almost random, but the rule is that you take the matrix, you write the first and second columns over to the right as columns 4 and 5. And then you do this. Well, maybe I'll do a duplicate. Okay, so we're going to add the products. along the 3 full diagonals that extend from upper left to lower right. So here's a template: plus sign, parentheses, plus sign, parentheses, plus sign, parentheses. I arrange it so that when you multiply down each of these, or down or up each of these diagonals, then you put the product inside the parentheses. Over here for the blue, again, you put the product along the line inside parentheses. So we add the product along the 3 full diagonals that extend from upper left to lower right, and we subtract the products. That's why we have the minus signs here, along the 3 full diagonals that extend from lower left to upper right. In order to remember that you subtract these products, that's why you put the minus signs in the templates. So after you get this template down, it's very easy. You take the product along each diagonal and put it in parentheses. Your only danger is an arithmetic error, a mechanical error. Okay, so this example, it was this one, all right? If A is the 3 by 3 matrix here, find the determinant of A. In other words, find this. And it's okay, if you're finding determinants, it's okay to write it like this without the brackets inside. This is okay. So again, according to Sarris's rule, you rewrite column 1 as column 4 and rewrite column 2 as column 5. This is what I showed before. You add the products along the 3 full diagonals this way, subtract the products along the 3 full diagonals this way. So within each pair of parentheses, you put the product along the corresponding diagonal. Right here, -1 times 2 times -1 is a positive 2 in there. This is easy. If you have a 0 on the diagonal, automatically the product is 0. Over here, -2 times 3 times -1 is positive 6 in there. We add these 3 products. The template does that for you. Over here, 0 here, that means the product 0. Over here, -1 times 1 times -1 is positive 1. Over here, -1 times 3 times 1 is -3. And then be careful as you unravel the signs. 2 plus 0 plus 6. And then, of course, you can ignore the 0. Minus 0, which we can ignore. -1, -3. I'm sorry, plus 3. This becomes a plus 3. That works out to 10. A number. A determinant is typically a number. If the matrix is full of numbers, then the determinant is a number, which here would have applications for volume, as we'll discuss later. Next up, the method you may have learned back in your old algebra class, finding determinants by the expansion by cofactors method, sometimes known as the expansion by minors method. Next time, try to remember.
Okay, questions. That's minors with an O. Questions. Do you remember determinants? Okay, they're usually numbers, but they can be expressions like e to the x or sine of x. All right, determinants. Next.
The general method for computing determinants is the expansion by cofactors method, which in principle you could apply to 4 by 4, 5 by 5, and so forth. Well, let's start with an example, because without an example, there's no point in talking. You got to see an example. Okay, the method works for square matrices of any size, but it's much harder for much bigger matrices. All right, example. Now, in fact, this is the same determinant, or the same determinant that we were talking about earlier, right? The same 3 by 3 matrix is here. We already found out it equals 10. So if you do this right, you're going to get 10, okay? So here's the idea. We're going to choose a magic row or a magic column. That's not what they're really called, but let's be cute, to expand along. We call it the expansion by cofactors method. Expanding, we pick a magic row or column to expand along. And you can, in principle, take any row or any column, but preferably one with zeros, because zeros really help a lot, as you will see. So in my example here, the best choices would be probably either column 1 or row 3. Here I choose the first column, column 1. So let's call that our magic column. Again, not really what it's called, but let's be cute. it helps, that 0 will help us a lot, as it turns out. Okay, and by the way, I'll call these the 3 magic entries. The 3 entries of our magic column are the 3 magic entries. Again, I'm being cute. Now, we've chosen the first column as our magic column. We could have chosen the magic row as well. Now, it's going to help to write out the corresponding sign matrix, at least the signs corresponding to the first column. The way that the sign matrix works, and we will need this later on, is that you're going to have plus signs on the main diagonal, and then you checkerboard, you alternate. Every time you move either right, down, up, or left, you're going to alternate sign. So here it's plus, minus, plus. We can take a walk, minus, plus, minus, plus, minus, plus. No 2 neighbors are the same sign, and it will always be plus signs on the main diagonal, not necessarily on the skew diagonal. Well, I guess we can't talk about a skew diagonal here, but this is like the longest skew diagonal. Yeah. That's not always the case. For example, in a 4x4, you'd have a minus up there. All right, we're going to need this thing later on. And again, since column 1 is our magic column, we're going to focus on these entries here. In fact, you could even erase the rest of this. You just need the ones here. Plus sign up here, it's on the main diagonal. Plus sign up here, then alternates minus plus. In general, the formula for the sign will be -1 to the I plus j, where I is the row number, j is the column number. Of course, a -1 corresponds to a minus, a +1 corresponds to a plus. Right. Here's the sign matrix for a 4x4. Here, the skew diagonal is, in a way, the longest skew diagonal, kinda, is all minuses. And it will be the same sign, either all pluses or all minuses, because you alternate here and here, for example. Again, here's the general formula. All right. Circle this again. I'll circle this too. All right, so now we're going to do expansion by cofactors or by minors. So the minors are going to correspond to the determinants of smaller determinants that we'll be working out. A cofactor would include the sign from the sign matrix. All right. Now, in the cofactor expansion, you're going to have one term corresponding to each of these magic entries. If an entry is a 0, then it's automatically 0. The term is automatically a 0. That's why we love 0. And if you have a row, if you have a row or a column of all zeros, the determinant is automatically 0. So if we had something like 0, 0, they look like 6s. So if we had something like 0, 0, 0 as our first column, I don't even care what happens in the rest of this 3x3 matrix. The determinant will be 0. But here, not necessarily, over here. All right, so the pattern goes for each of these 3 magic entries, not really him though, you're going to get a term. Each term consists of the sign from the sign matrix, which we get over here, the magic entry, and the corresponding minor, which I'll explain later. The minor is the determinant of the submatrix, the smaller matrix that you get when the row and the column containing the magic entry are deleted. Okay, so how does that work? So it's right here. We're going to expand along the first column. Now, the signs from the sign matrix, they go plus, minus, plus. So the signs from the sign matrix go plus, minus, plus. The magic entries go -1, 3, and 0. I'm setting up this template. The submatrix is the hardest part. Here, I copy the 3x3 matrix here and here, which may be overkill, but I want to show you what's happening. The idea is that you should be able to do this problem without having to write the entire matrix out, but I want to show you what's going on. Okay, so for this first minor, for this determinant here, we take the original 3x3 matrix and we delete the row and the column containing the magic entry we're looking at. We're looking at -1. The -1 goes here. Over here, we cross out the row and the column containing the -1. And we take the determinant of this submatrix. Then we have a minus sign times the 3 here. That's our next magic entry. Times the determinant of, we delete the row and the column containing the 3. We're always going to delete our magic column here, by the way, because it contains the magic entries. And we'll take the determinant of this submatrix. Plus 0 times, well, who cares anyway? I mean, it'll be some number, but this product here will be 0. And the term here will be 0. All right. So now we're down to these. I've cleaned these up. So now we have to find the determinant of this 2 by 2, which reminds you of butterfly. The product along the main diagonal minus the product along the skew diagonal. -2. Again, personally, I like to write products instead of writing too much out, but -2 minus -1. 1 times -1 is -1, right? -2 plus 1 becomes -1. All right. Product along the main diagonal minus product along the skew diagonal. All right. Now, over here, product along the main diagonal, -1. Minus product along the skew diagonal, 2. And that's -3. All right, let's bring it all together. -1 times -1 minus 3 times -3. And by the way, the fact that these numbers look a lot alike, it's a coincidence. It's not always like this. But the answer is 10. 1 plus 9 is 10. The same as before, of course. And by the way, there is a way that you can use EROs to help you find determinants. You'll be taught that in Math 254, linear algebra. So for example, let's see, row replacements, the rescaling and addition method that preserves determinants. For example, if you add this row to this row, you get this all 0 row, and you know the answer is 0. Every time you switch rows, that leads to a sign flip. And you can factor a scalar, a non-zero scalar, out of an entire row or an entire column. It's like a factoring here, out of a single row. But again, that won't be really in our class. You'll see these in Math 254, linear algebra. Again, if a square matrix has a row or a column consisting of all zeros, its determinant is 0, like this guy. And if you have a matrix in triangular form, either upper triangular or lower triangular, then the determinant is the product along the main diagonal. In this case, 2 times 3 times 4, or 24. Does not matter what these are. And it makes sense because if you were to do cofactor expansion, it would be plus the 2 times plus 3 times positive 4. 2 times 3 times 4. Now for this 4 by 4 beauty, normally a 4 by 4 would be very hard to do, but there's a clear choice for which row or column you want to expand along. Which magic row or magic column would you choose? I would choose row 2, otherwise it'll be a lot more work because there's only one term to really deal with here, which corresponds to the 3. But wait, I need the Sine matrix, or at least the relevant signs from the Sine matrix. Well, here's the thing. Now, in general, we're going to get 4 terms from this cofactor expansion because we have 4 numbers here, but 3 of those terms are going to be 0. This is the only one that's really relevant. What's the sign from the Sine matrix? Well, we know we have a plus sign here. Along the diagonal, same sign, plus sign. So that means for the 3, you're going to have a minus sign. All right. So you will have to do a sign flip there. There's a negative sign indicating a sign flip. Or you can walk like this, positive, negative, positive, negative. Okay, so we have the negative sign from the Sine matrix. The number here, the magic entry, the only one that's really relevant, the 3, and the determinant of the row, the submatrix you get when you delete the row and the column containing the magic entry. And you can attack this with either Saras's rule or another cofactor expansion method. Turns out this determinant's 2. Negative 3 times 2 is negative 6. Of course, work this out. Now, next up, I'll just have a brief discussion of cross products, which will not be on your homework or exams, but it's something that definitely comes up big time in calculus with analytic geometry 3, Math 252. More of the analytic geometry part next time.
Okay. So again, the next video is optional, but it's a key application of determinants, or really pseudo determinants, right? So that's gonna be the next video.
Hi, everyone. This last part in 8.4 is optional, but you're going to see this a lot in Math 252, calculus with really analytic geometry 3, where you deal with 3-dimensional things. Now, we talked about the dot product of 2 vectors in R whatever, R2, R3, R4, based on the number of components you have. But in 3 space, there's also a cross product or vector product. So if you have 2 vectors A and B, right? So this vector A, number, comma, number, comma, number, vector B, number, comma, number, comma, number. A cross B can be constructed as follows. So you have these bars for determinant. It's really called a pseudo determinant because you're not supposed to put vectors in here, but we have vectors in here. I is 1, 0, 0. I mentioned this before with vectors. J is 0, 1, 0. And K is 0, 0, 1. So in 3 space, we often draw I like that, J like that, and K like that. We often orient the coordinate axes like so with the corresponding vectors. And then you put vector A in here, the components. You put the components of vector B down here. And then you basically work out determinants the way you would normally do by Saras's rule or maybe cofactor expansion, except you're dealing with these vectors in here, which is kind of weird, but they go along for the ride, right? And the idea is that, well, let's say vector A is here, and vector B is here. Then A cross B might be like this vector here. The cross product vector might be like this. It's orthogonal or perpendicular to both vectors here. And it's very useful because if you consider the equation of a plane, so here's a plane. Well, if you know a point in the plane, and if you know 2 vectors, quote unquote, in the plane, okay, then you get an equation for the plane. From these 2 vectors, you get a cross product. It's kind of like the term joystick has been used, like the old joysticks from video games, where, or like a controller, where you have your point, and then this is like well, it's like a gear shift almost, or a joystick in the old Atari consoles, where you can kind of move this thing around. Okay, but the idea is that you get the equation of a plane. So you use cross products a lot in Math 252 because you often need these perpendicular vectors. They're called normal vectors. We use normal a lot. That's a normal vector to the plane. Now you could have taken the vector B cross A, which means you switch these rows, and actually that would be in the opposite direction. B cross A would be in the opposite direction, same length, point in the opposite direction. The cross product is anti-commutative. B cross A is the opposite of A cross B. So not on the test, but you're going to see this a lot in Calc 3. And also I want to show you another product, another way to multiply vectors aside from the dot product. Okay.
Any questions so far? Because actually, these last two videos, this one and the next one, they're optional. So the previous video was the last required one. Okay. Next, I'm going to show you applications of determinants. Again, it's optional, but yeah, it's cool. So you'll see it's short. It's like 2 minutes, and then I'll go on to the homework questions.
Hi, everyone. Quickly, an optional section for everyone. Section 8.5, applications of determinants. Kramer's rule is a method that uses determinants for solving systems. As a practical matter, it's rather nice for systems of 2 equations in 2 unknowns, but for 3 equations and 3 unknowns, it's rather unwieldy. You're probably better with something else. But Kramer's rule is a method that uses determinants to solve systems, and you can check it out. Again, for the 3 equation case, it may not be worth it. But more interestingly, area and volume. So here's the deal. Let's say that I take the position vector 2, 0 in red, the position vector 0, 3 in blue, work out the determinant, you get 6. Guess what? That's the what of the rectangle? The area. This thing here, there's a shearing effect here as a parallelogram. Still, 2 times the height 3 is 6. That's still the area. If the determinant turns out to be negative, then you take the opposite. So in general, you take the absolute value of the determinant to find the area of the parallelogram determined by these position vectors. If you want to find the area of a triangle, you can take half. And again, if the determinant's negative, you take the absolute value and you get the area. Here, these vectors are collinear. Here they point in the same direction. Determinant is 0. Well, there's a degenerate parallelogram. There's no real area here, 0. This generalizes through to 3 dimensions. So if you have 3 position vectors in 3 space, they determine a parallelepiped, this prism thing, and the absolute value of the determinant will give you the volume. All right, pretty cool.
All right, so that's that. Okay, I was going to show what the purpose of some of this stuff was, right? Areas and volumes, very natural applications there. All right. Okay, so, well, hey, for many of you, have a great break, and we'll reconvene Tuesday after break, okay? But I know a lot of you have questions. So for many of you, okay, well, have a great night, have a great week, and I'll see you after the break. I will be around, but I know some of you had questions. So why don't we do this? See, it's 9:24 now. I'll give you 3 minutes to kind of look things over. Let's reconvene at 9:28 in 3 minutes, okay? 9:28. In the meantime, okay, 9:28. In the meantime, go ahead and put in any questions you might have. All right, so 9:28. So either, like homework questions or actual questions, all right? And I am continuing the recording. All right. In fact, I am going to continue the recording. I'm not going to pause it. I'll just continue it. All right. Okay. So we'll reconvene at 9:28. Okay, so now I'm going to set up my tablet. Okay, so the good time to use a tablet, certainly for matrices. Okay, so I'm going to set this up. All right. All right. Okay, so setting up here. Okay, so now again, I'm continuing to record, but if you want me to pause the recording, just let me know. All right, so let's go back to the beginning. All right, so 7.1 number 2. All right. Okay. Oh, let's start with purple. All right. Okay, so 7.1 number 2, that's going to be over here, right? Okay. Okay, so let me okay, so I'm going to move this over here then. All right. 7.1 number 2. Okay, so this one, right? And by the way, I did number 3 in the Tuesday video. Okay. Maybe I should make this I'll make it green. All right, let's make it green here. All right. So over here. All right. So 7.1 number 2, right? Okay. All right, so that's that one, right? Okay, so 7.1 number 2. So A, find the solution set of the system. All right. Okay, now this is very naturally set up for what technique? Well, we don't have too many like terms here, so I wouldn't recommend the addition elimination method. This is prime for substitution, right? Which totally makes sense because as it stands, right, we have here y as a function of x, right? And we take this thing here, the x plus 2, plug it in, right? But it's easy to mess up the algebra, right? Okay, so what's happening? When you plug into the first equation, you're going to get, you're going to get x squared plus the square of y, which is the square of x plus 2, okay, equals 2. Right? On the left side, we have x squared plus, be very careful, the square of x plus 2. Is that just x squared plus 4? That's wishful thinking. Twice the product of the two terms, the 2ab term. Twice the product of the two terms, 2 times x times 2 is 4x. That's the PST here. X squared plus 4x plus 4. Don't forget the 4x. A lot of people forget this.
Professor, I found what I did wrong.
Oh, okay.
I wrote the equations wrong, which is why I was never able to get it.
Oh, okay. But I would like to ask the other students, would anyone like me to proceed?
You can keep going. I just wanted to point that out, that I just realized I wrote the thing wrong, which is why I can't get the right answer.
Okay. Well, I'm sure many students and students watching would like me to finish, so that's fine. Okay. So then we have x squared plus x squared is 2x squared. All right. Usually people mess up here, plus 4x. All right. I'll go ahead and subtract 2 from both sides. Plus 2 equals 0. Because if you have a mix of like x squared and x terms, it's probably a good idea to isolate 0 on one side. All right. If we didn't have this, then the square root method might work. But we have an x squared term and an x term. I think isolating a 0 would help. By the way, we can divide both sides by 0. But divide both sides by 2. Sorry. Divide both sides by 2. X squared plus 2x plus 1 equals 0. And this itself is a very famous PST. It can be factored as the square of x plus 1. Or even if you use the guess method, it would be x plus 1 and its twin, right? Equals 0. Well, this happens only if the base here is 0, right? You don't even have to write this part. This happens only if x plus 1 itself equals 0. Subtract 1 from both sides, x equals -1. I'll circle that. But we're not done yet. We're not done yet because we have a system in x and y. So for any solution, if we get an x coordinate, we better find the corresponding y coordinate. Fortunately, we already have y solved in terms of x here. So I can just use this guy over here. I usually call him star, right? So let's plug in the star. Y equals x plus 2. X is -1. I'll put an arrow here, right? Plus 2, right? Y equals x plus 2 from the second equation, right? So therefore, y equals +1. So if x is -1, y is +1. That's our only ordered pair. Now, usually it's nice to check, but especially if you have like y is a function of x, then it's usually not as necessary. And also, we can kind of verify with a graph whether or not we think we have the right number of solutions. So we think this is the solution set, right? The solution set with the ordered pair -1, 1. X first, and then y. Make sure it's in that order. And you can check. Not just my answer sheet, but you can check in the original system, right? That's part A. In part B, use the solution set from A to graph the equations. Because here's the idea. X squared plus y squared equals 2. That's a circle of radius √2, right? In the xy plane. But then you might go, okay, y equals x plus 2. That's a line. How is the line intersecting with the circle? Well, the solution set suggests only at one point. And it's going to be one point in quadrant 2, -1, 1. This is going to be a tangent line. All right. So that's the picture, right? Graph the equations. That's the picture. Now, Desmos does a nicer job of it, of course. Let me go to Desmos here. Okay. So going to Desmos, all right. So x squared plus y squared equals 2. That's a circle of radius √2. And then we have, it was y equals x plus 2, right? And you can see here that, again, this blue line is a tangent line to this point, -1, 1, right there, -1, 1, which is the intersection point between the circle and the line, the sole solution for the system, graphically. All right. Any questions there? Any questions there? A worthwhile problem. I'll go ahead and save this. All right. This is one number. All right. Any questions about this? All right. So let's see here. Now, 7.1 number 3, that was in the video from Tuesday. So I'll go ahead and postpone that for now. Yeah, watch the recording. Right. Okay. Although I can do it later if anyone wishes. Okay, so now looking at this JPEG here. All right. Okay, so I presume we're looking at 8.1 number 8.
Yes.
Wait, number 8, is that right?
Yep.
Okay. Let me go ahead and circle that. Okay, and let's do this in blue.
Yeah, I don't necessarily need to go over the whole problem. I just want to make sure that the way that I'm doing the EROs is acceptable, where I'm not necessarily saying like R2, showing R2, and then showing what I'm subtracting from it, and then showing it again. I'm just showing the results.
You got the right solution, it looks like, right?
Right. Yeah. I'm confident that I got through the problem correctly. I'm just making sure that I'm showing sufficient work. Is just
Right.
the one I wanted to confirm.
Now, by the way, really, you should write the original augmented matrix. And by the way, it's okay if you append. It's okay if you squeeze it in here, or if you attach a little sheet of paper, a little half slip. But technically, you should start with the original augmented matrix, where your row 2 here is back at row 1. You should write the original augmented matrix, actually. So you would start with 0, 1, negative 2, 14 as your top row, and then 1, 0, 1, negative 3, and then 4, 0, 6, negative 22. Again, you can kind of squeeze it in here, but you should technically start with the original augmented matrix. And then I see that you switch row 1 to row 2, right? Good idea.
Yeah. Would it be all right if and I did this on one of the other problems, if I just wrote that they were switched, like as a note?
Well, technically, for a full job, especially since part of my purpose here was that I wanted people to write this nicely, and then from that get a good augmented matrix. So technically, and again, you can attach a half slip or something, or just
System.
electronically. It's easy because you just have to scan whatever. But technically, I would recommend rewriting the system so you line up the like terms and then write the first augmented matrix. So I'd like you to prep it a bit more.
Okay, I did rewrite the system. It's right under it, actually. It's under it because I added it in after.
Oh, okay. So basically you, but you still switched. Okay.
Yeah. So just the step in between rewriting the system and then writing the matrix in that format.
So I will say this, that again, technically, for a full complete solution, I would recommend that you write the original augmented matrix for the given system, right?
Okay, yeah, I see. I have it switched in that one too as well.
So that's the one, and then again, you don't have to write the steps, although I would recommend it because then we can debug. Actually, I'm going to go ahead and say, go ahead and try to put the steps in. I'm not going to grade on the writing of your steps, but it's helpful, right? Okay, so you switch row 1 and 2, and then get that right. And for something like this, now of course I'll accept this. You don't have to write out the table, but I think my table method was, you're kind of doing it here, right? Where the row you're changing is on top, I guess, and then.
So it's just the result of the operation. So that's the result of row 3 plus row 1.
Oh, okay.
Negative 4.
So you're doing that in your head, which I would accept. I don't recommend. It's really easy to mess these up, but as far as work shown, I mean, given that you're doing this in your head, then I would encourage you to write something like this so that I get a sense of what you're doing. Right. So, I think you're pretty good, basically, where you're indicating what you're doing, and I guess you're doing a lot of the arithmetic mentally, right? And then you do that. Although,
I can reference over to the table as far as like I can see. Okay, R3 is right over here, and R1 is right over here, and then just show the result over here. And I can understand what you're saying as far as like it being helpful to me to write out more steps to make sure, especially as the matrix gets larger, to make sure that I don't get confused. But I just want to make sure that I'm not getting myself marked down for not putting stuff in there, even once I have gotten to the right answer.
What you have here is good, but you're giving me a it's about as sparse.
Okay, that's what I figured. I was kind of on the borderline, and that's why.
So it's acceptable. It's very sparse. So I had to kind of look at it. So so if you're gonna do this, that's fine. If you indicate the step to me and then okay, you're doing that.
I just don't want to get marked down for points.
Yeah.
I'm a little lazy with my work, and I can show a little bit more.
So and like I was saying in the lecture, it's preferable to it's preferable to rewrite the matrix every time you apply a different type of ERO, because here you have like a row replacement, an addition, elimination, and what was that? An addition rescaling step here, and there's a rescaling. So my recommendation in lecture was that you should rewrite. You should write the new matrix after you try a different type of ERO. I don't think I mark you down here because I see what you're doing, right? It's like, so you have the. Okay, so you're copying the row 1, and you're changing the row 3. Right. So I guess I might have recommended putting the arrow down here actually, but
well, the arrow is just for the overall matrix. I kind of throw those in at the end because they're not all in the same location. So like and like 8 goes left to right, but 9 goes like from the matrix over to the EROs and then back over to the matrix.
Oh,
I figured,
yeah.
oh, I better throw some arrows to just
Yeah.
show the flow of the problem.
So I would say that what you have here is really, really sparse. And in terms of my recommended solution, you really should write more matrices where yes, you do have to copy rows a lot. But remember, my recommendation is that every time you certainly try a new type of ERO, you should write down the new matrix. But what you have here, you do indicate the back substitution, right? Yeah, you do indicate the back substitution. So yeah, you really have the bare bones of what well, don't forget the original augmented matrix, but certainly if you add on the additional augmented matrix, I believe you would have enough for full credit. But again, this is really sparse. It's about as basically stripped down as as a solution as I might accept for full credit if you give the original augmented matrix out.
Okay,
here.
so make sure the original matrix gets put in there, and then these solutions will be acceptable. And then in the further ones that I still have to do, I'll just
For full credit. But again, I do recommend you write things out. I think that helps. It would actually help you if you actually write things out more.
Okay.
Yeah.
Yeah, I think I was just running out of space, and I think we already talked about it. Where it was
Well, the thing is that these were meant to take up
trying to compact everything.
these were meant to take up a lot of space. They're meant to take up a lot of space. So typically, these would take like a whole side of a sheet, typically, right? And you're condensing it down to like just a few lines. So you're taking kind of a risk, but at least you are clearly indicating your steps. You really should be rewriting your matrix from time to time as a matter of good practice.
Okay.
So like I said, my sense is that I would probably give you full credit, but I can't even fully guarantee it. It depends on what I see here. I have to look carefully at the problems I grade.
Mm-hmm.
Yeah.
Yeah, I'm confident that it's all correct. It's just like we've talked about, it's a little bit sparse as far as I'm not.
Right. But based on what I'm seeing, based on what I'm seeing here, I mean, assuming that your answer is correct and your work was reasonable getting there, I'm not. I doubt that I would slash a whole bunch of points. I might nick you by a point or two if I really sense that you're skipping too much in the middle or something. But I get the sense that you can get an A on the last homework if you keep this up. But still, I do recommend that you spread it out. So the work you do from now on, I encourage you to spread it out.
Yeah, definitely not do that.
And again, put the original augmented matrix as well for the original system, because I have the right to mark you down if you don't do that.
Okay, got it. I'll do that.
Yeah.
Okay, thank you.
You're welcome. Yes, and we can come back to this also.
I think that's it. Everyone else is bounced out.
Oh wow. Okay, yeah. Okay. Well, a lot of people still have to really work their homework. A lot of people are going to be busy next week. Yeah. I'll be grading. Yeah. Well, you're right. It's just you and me. So, well, do you yourself have any questions right now?
No, I think that was it. Just wanted to make sure that I was showing my work correctly. So
yeah, try to spread out a bit and show you the first augmented matrix. So that's my recommendation. Yeah.
Okay. All right. Have a good night, Professor.
Have a good night. Have a good week. Yes.
All right. You too.